Welcome to the next video in the GRE Math Subject Test video series. We're grabbing another random problem, and this one asks us to consider sum two two-dimensional subspaces of R to the 4 and asks us what the possible dimensions of their intersection is. Now, I'll just go ahead and directly give you the fastest answer to this question, which would be, well, look, if V and W are both the same two-dimensional vector space, then certainly their intersection could have dimension 2. So we can already eliminate some answer choices. It has to be smaller than 2, so we know that you cannot have a dimension bigger than 2. And from here, we could say, well, here's a really quick demonstration that they could, in fact, have dimension 1, or the intersection could have dimension 1. V could be equal to the span of the following very simple elementary vectors. And then W could be this other span. And then it's very easy to check that the only vector shared between them is the 0 vector, so that space has dimension 0. So that's a quick demonstration that it could have dimension 2, it could have dimension 0, and it wouldn't be too hard to give an explicit reason why it has dimension 1, but for the purpose of the exam, why would you bother? That's a very fast, a fast answer to the problem without using anything fancy, I guess, right? Like without using theorems, just thinking about it directly. I guess that's the solution that I wanted to start with. But if you want to know of other solutions, right, maybe you want to be aware of some of the sort of surrounding context of relevant theorems, just in case some other problem was similar but possibly a little trickier, like what if it was R3 rather than R4, then you might want to know of some other ways to think about this problem. Now, let's just say if it were R3 rather than R4, then again, right, V and W could be the same space, and so again, their intersection could have dimension 2. And I'm going to reason about this again, right, not using the obvious, right? There's a theorem here that is kind of the obvious theorem to appeal to, and I'll get to that eventually, but I want to kind of like approach this in stages. So another way that you could think about this is, okay, so we know that it could be two-dimensional. Could it be one-dimensional? Well, you could think, well, maybe W has a single vector that is independent of the space V, and so, and in that case, their intersection, would not have, the space of that one vector, and so then the vector would be one-dimensional, right, as a quick argument. But what about zero-dimensional? Well, if we try to do the same thing, but think about when W has two vectors that are independent of V. Well, that would run into absurdity, because if V has two dimensions already, and then W has two independent vectors that are independent of V, then altogether you put those vectors all together into the same span, and you get a four-dimensional vector space, which cannot possibly be in R3, because remember, we were thinking of R3 for example. So anyway, so the same reason, right, like you have to be a little bit careful about the reasoning. And so one way to be a little extra careful is this theorem, right? So you could just directly think of the intersection, as I just did, and you will still get to the right answer. But, you have to be careful. And so a formula that you often don't have to be quite so careful with is this formula. And if you had a good linear algebra class, then hopefully they discussed this during your class, but it says that if you want to know the dimension of the intersection, then you have this relatively simple formula relating it to the dimension of the sum, right? So the dimension of the intersection is the dimension of dimV plus dimW minus dim of the sum. And that's just the regular sum, right? That's not like the the direct sum or any fancy notion of sum. That's just taking all the vectors in V plus all the vectors in W. Now, so we're interested in this, but we use this formula instead. Obviously, they're already giving us 2 plus 2 and then minus some quantity. But I claim that it's just a little bit easier to think about what happens to the dimension of the sum than it is to try to think about the dimensions of the intersection. So again, we're going to take the perspective that we're starting from V, but we're imagining that there are various vectors in W that are independent of V, and there could be either 0, 1, or 2 vectors. Now I'm going back to the case where we're sort of living in R4, right? So I'm going back to considering R4. And so again, right, we think that if V has 2 dimensions, then the dimensions that the sum could, the dimensions that the sum could have, I'm writing this inaccurately. So we know that if W is like the, nothing at all, or right, a 0-dimensional space, right, the space of just 0, then the dimension would be 2, right? Because V has dimension 2. If W has dimension 0, then you just get 2. Now consider what if, again, starting from V, which has dimension 2, and W has 1 extra independent vector, then the dimension of the sum is going to be 3. And then if W has 2 independent vectors, which again is possible in this scenario because we're dealing with a 4-dimensional space, but we know that we have to stop there, right? W couldn't have 3 independent vectors independent of V. So these are the possibilities, right? These are all the possibilities for the sum. And you can check that what we're essentially saying is that you could have 4 minus 2 or 3 or 4, and this is the same thing as you could have 2 or 1 or 0 dimensions for the intersection. So hopefully that gives just a bunch of useful information, a bunch of things that you can use to help you quickly and reliably solve a problem like that.